Now let us see the energy in simple harmonic motion. Let us take an example of a pendulum. This is one extreme position. And let us take example of this spring also. Now, as we know, the pendulum will start from position x is equals to 0 and gradually it will be displaced from its mean position towards x is equals to a and towards x is equals to minus a. Now, as a reference, we are taking the potential energy at this point to be 0. So, this pendulum will rise some height compared to the mean position. So, as pendulum bob starts moving towards the extreme position, its height will increase compared to the reference level. So, its potential energy will increase. As it starts moving, there will be restoring force acting on the object. As the angle increases, the restoring force will also increase. At the extreme position, the potential energy will be maximum. And at this point, we know that velocity will be 0. From this equation of velocity position, v is equals to omega under root a square minus x square. At x is equals to a, we know that velocity is 0. So, at the extreme position, the velocity will be 0. As velocity is 0, kinetic energy will be 0. Now, at x is equals to 0, the velocity will be maximum, that is equal to a omega. So, at x is equals to 0, velocity is maximum, so kinetic energy will be maximum and potential energy will be 0. So, here we can see that as the pendulum bob starts moving towards upward, its kinetic energy keeps decreasing and potential energy keeps increasing. At the maximum displacement point, at the extreme point, the potential energy will be maximum and the kinetic energy will be 0. Now again it will start to move towards mean position. Gradually its velocity will be increasing, so potential energy will decrease. Again at x is equals to 0, potential energy will be 0, kinetic energy will be maximum. Now it will move towards the another extreme position. Same thing will happen, potential energy will increase, kinetic energy will decrease. At this point x is equals to minus a, velocity is 0, again it will start to move in this direction. So, here we are not considering any dissipative forces. no dissipative forces are considered. Same thing we can see in the spring mass system. Here in the pendulum system it was gravitational potential energy. In the spring mass system it will be elastic potential energy. At x is equals to 0, the spring is in its natural length, so there will not be any energy stored. When we stretch it, by distance a, then there will be restoring force in this spring, and due to that restoring force there will be some elastic potential energy. So as we increase the elongation, the elastic potential energy will increase and the kinetic energy of the block will decrease. So we can conclude these things as at x is equals to 0, potential energy is taken 0 and kinetic energy is maximum. The maximum kinetic energy is half m Vmax square, and we have seen that maximum velocity is a omega. So maximum kinetic energy will be half m a square omega square. And at x is equals to 0, x is equals to a, or x is equals to minus a, kinetic energy is 0 and potential energy is maximum. Now, as we have not considered any dissipative forces, the total mechanical energy, there is no external force acting on the system, so total mechanical energy of the system is conserved. So we can see that kinetic energy plus potential energy is always constant. And that will be equal to K max, that will be equal to PE max, and that is half m a square omega square. We can prove this mathematically. Let's say the position equation of a particle executing SHM is given by x of t is equals to a cos of omega t plus phi. Omega is the angular frequency, a is amplitude, and phi is initial phase. So its velocity will be d by dt of x of t, that will be equal to a omega sine omega t. Now the potential energy is given by half kx square, so that will be half k a square omega square a square cos square omega t plus phi. So potential energy will be half k a square cos square omega t plus phi. The kinetic energy is half mv square, that will be half m a square omega square sine square omega t plus phi. But omega is equals to under root k by m. So omega square m is equals to k. So we can write this kinetic energy is equals to half k a square into sine square omega t plus phi. So the total mechanical energy will be potential energy plus kinetic energy, that is half ka square cos square omega t plus phi plus half ka square sine square omega t plus phi. Taking this half ka square common, cos square omega t plus phi plus sine square omega t plus phi. So total mechanical energy will be cos square omega t plus phi and sine square omega t plus phi will be 1. So total mechanical energy will be half ka square. From this equation, we can see that total mechanical energy is independent of time. So at any time instant during the motion, the total mechanical energy will be constant. Now let us plot the graph of energy versus position. Here we are plotting graph of both potential energy and kinetic energy with the position. Let us take the reference of the pendulum. This is x is equals to 0, x is equals to a and x is equals to minus a. As we have said, at x is equals to 0, for a reference we have taken potential energy as 0. So this will be 0. As we gradually move towards either side, towards positive or towards negative a, the potential energy will increase. So the potential energy is increasing. The potential energy is given by half kx square. So we can say potential energy is directly proportional to x square. That's why the graph will be parabola. At extreme position, x is equals to a and x is equals to minus a, the potential energy will have maximum value, and that maximum value will be half ka square. Now, as for the case of kinetic energy, at mean position, kinetic energy is maximum. So at mean position, x is equals to 0, kinetic energy is maximum. As we move towards either side, x is equals to a or x is equals to minus a, potential energy increases and kinetic energy decreases. So kinetic energy is decreasing, again it is decreasing parabolic manner. At x is equals to a and minus a, the velocity is 0. At extreme position, as velocity is 0, kinetic energy will also be 0. So kinetic energy will be 0 at extreme position and potential energy will be 0 at mean position. Now let us see the variation of either of energy, potential or kinetic, with the time. Let's say this particle is starting its oscillation from mean position. So it will take capital T by 4 time to reach up to height and extreme position A. This time will be T by 4. Again it will come to this point and this time will be T by 4. So at T is equals to 0, the potential energy was 0. At T is equals to T by 4, potential energy is maximum, and after again next T by 4, the potential energy is 0. So the value of potential energy is repeating after total T by 4 plus T by 2, that is equals to T by 2 times. On the opposite side, scenario will be same. From x is equals to 0 to x is equals to minus a, time taken will be T by 4. From minus a to 0, time taken will again T by 4. At this point, potential energy will be maximum. So if we draw the graph of potential energy versus time, then at T is equals to 0, the potential energy is 0. Then it will increase up to maximum height and again it will be 0. This time will be T by 4, this time it will be T by 2. Again it will increase to maximum height and again it will become 0. So the time period for potential energy will be T by 2. Now let us see the same case for kinetic energy. At x is equals to 0, the velocity is maximum, so kinetic energy will be maximum. After time T by 4, velocity is 0, so kinetic energy is also 0. Again after next T by 4 time, the object will be at mean position, so kinetic energy will be maximum. So again the kinetic energy's value is repeating after T by 4 plus T by 4, that is T by 2 times. Let us draw the graph for kinetic energy and time. At T is equals to 0, the kinetic energy is maximum. Then gradually it will decrease. Again it will be maximum. Again it will decrease. It will be maximum at mean position. So this is T is equals to 0, this is T is equals to T by 4, and this is T is equals to T by 2. So again time period for kinetic energy is also T by 2. From this we can conclude some points. If time period of SHM is T, then time period of kinetic energy and potential energy will be T by 2. If frequency of SHM is F, then the frequency of kinetic energy and potential energy will be frequency is given by 1 upon time period 1 upon t by 2, that will be 2 by t, but 1 by t is equals to f, so that will be 2f. So the time period of energy is half that of the time period of SHM, and the frequency is double that of the SHM. Now, what is the time period of total mechanical energy? The total mechanical energy is always remains constant. So if we draw the graph of mechanical energy versus time, then we'll get this. So the time period of total mechanical energy is infinite. So remember this points, it will be very handy for the solving problems. Now let us find a point where potential energy and kinetic energy are equal. We know that the total mechanical energy is equals to potential energy plus kinetic energy, and that is always constant, and that is equals to half k a square omega square. If potential energy and kinetic energy are same, then we can write this to be equal to 2 times of kinetic energy is equals to half k a square omega square. This will be m. Let's say the point where kinetic energy and potential energy are equal, the velocity of particle is v and x is the position from x is equals to 0. So the kinetic energy at that point is given by half mv square, that is equals to half m a square omega square. This half m will get cancelled out, so we can write 2v square is equals to a square omega square. Velocity as a function of position is given by v is equals to omega under root a square minus x square. So v square will be omega square into a square minus x square. So put this value 2. V square is omega square into a square minus omega square into x square is equals to a square omega square. So 2 omega square a square minus omega square x square is equals to a square omega square. This omega square will be cancelled out, so we can write 2a square minus x square is equals to a square. So x square is equals to 2x square is equals to a square. So x square is equals to a square by 2, and x will be equal to a by root 2. So at x is equals to a by root 2, potential energy and kinetic energy will be same, and that will be equal to half of the maximum kinetic energy, that is 1/4 of k a square. Let us say an example. a particle executes SHM with amplitude A and time period t. When the displacement from equilibrium position is half the amplitude, what fractions of the total energy are kinetic and potential? Here it is given that x is equals to half the amplitude, so we can write plus or minus a by 2. Let's say total energy is E, that will be equal to half k a square. Now the potential energy will be half k x square, that will be equal to half k a by 2 whole square, that will be half k a square by 4. But this half k square is E, so potential energy will be E by 4, that is 25% of total energy. The total energy is potential energy plus kinetic energy. So kinetic energy will be 100 minus 25, that will be 75% of total energy. So till now, whatever oscillations we have considered or whatever SHM motion we have considered, in that we were not considering any dissipative forces. That means the total mechanical energy is always conserved, that is always constant. These are the cases of ideal oscillations. This kind of ideal oscillations are called undamped oscillations. In the case of undamped oscillation, say for example for a pendulum, once the pendulum starts its oscillation, there is no resistive force, so it will continue to move in this direction for infinite period of time until and unless some external force is applied to stop it. Its amplitude will not change, its amplitude will be constant with time. So if we draw the graph for amplitude versus time, then, or the displacement versus time, then the graph will be like this. The maximum amplitude is not changing. But this kinds are ideal oscillation. Practically the situation is different. We know that practically certain forces are acting at resistive force, at resistance and etc. So once the oscillation starts, gradually the maximum displacement of this bob will decrease, and after some time this bob will come to rest. This kind of oscillations are called damped oscillations. These damped oscillations are the practical oscillations, we can say. In this kind, the amplitude will gradually decrease. So, the graph for displacement versus time, the amplitude will gradually decrease and it will become 0 after some time. So we can see with the time the maximum displacement that is amplitude of the oscillation is gradually decreasing, and after some time it will become 0. So now let us see mathematically what happens in the damped oscillations. In the damped oscillations, there will be some dissipative force, mostly due to air friction. So force due to air friction is called drag force, and from the Stokes law we know that fluid friction is minus 6 pi eta r v. So we can say that Fd is directly proportional to the velocity. So Fd is equals to minus of Vv. It will be in the opposite direction of velocity, so this negative sign is used. This V is a positive constant and it depends on the characteristics of medium. We can see it is dependent on viscosity and the size of or the shape of the block, that is radius. Now, when the mass m is attached to a spring and released, the spring elongates little and the mass settles at a position. This is the equilibrium position of mass. Now, if mass is pulled down or pushed up a little, the restoring force will act, and that restoring force will be equal to minus kx. So, the total force can be written as minus kx minus bv. But force is mass into acceleration, so m into a of t is equals to minus k x of t minus b v of t. So a can be written as d square x by dt square equal to kx plus v can be written as dx by dt is equals to 0. Rearranging it proper order, so d square x by dt square plus b dx by dt plus kx is equals to 0. This is the formula, or this is the equation describing damped oscillations. The solution of this equation describes the motion of block under the influence of damping force. So if we solve this equation, we will get x of t is equals to a e power minus bt upon 2m into cos of omega dash t plus 5. From this equation, we can see as time increases, this power will increase and the amplitude will decrease. Here, A is the amplitude, initial amplitude, and omega dash is the angular frequency of the damped oscillator. Omega dash is given by under root k by m minus b square by 4m square. As the amplitude is decreasing, the energy of the oscillator will also be decreasing. So energy as a function of time is given by half k a square e power minus bt by m. So this will be the energy of damped oscillation. There are two types of damped oscillations. The meaning of damped oscillation is they are practical. The amplitude will gradually decrease. That are free oscillations and forced oscillations. The meaning of free oscillation is once the oscillating motion has started, we will not apply any external force to maintain the oscillation. So gradually the amplitude will decrease and finally after some time the object will be at rest. So in the free oscillations, no external driving force is acting. But in case of forced oscillation, to maintain a certain amplitude, we will constantly apply some force. So, in the forced oscillation, there is driving force acting on the object. Let us understand forced oscillation with an example. A person is sitting on a swing and the other person is pushing him from the back side. If we start on swinging, or the person sitting on the swing start on swinging, and after some time if he stops to apply any external force, then gradually the swing will come to rest. But if the other person standing outside, standing behind him, will continue to push him every time the swing comes in the back direction, then the swinging will continue. The amplitude of the swing will not change. So the force applied by the person standing behind the swing is called the driving force. The purpose of the driving force is to maintain the amplitude. The free oscillations will die eventually due to damping forces. But in the case of forced oscillations, they are maintained by the driving force and external energy. Let's say the external force acting f of t is f naught cos of omega d t. Here f naught is the magnitude and omega d is the frequency of driving force. Now, in addition to the drag force and the restoring force, this driving force is also acting. But the function of drag force and restoring force was to decrease the amplitude. These two are used to decrease the amplitude, while the f of t is used to increase the amplitude. So the net force MA is equals to minus of K x minus of B V plus F naught cos omega d t. So MA plus Kx plus BV is equals to F naught cos omega d t. So we can write M d square x by dt square plus b dx by dt plus kx is equals to f naught cos omega d t. So this will be the describing equation for the forced damped oscillations. Now, if we find the solution of this equation, then x of t will be equal to a cos of omega dt plus phi. And the amplitude as a function of f naught and omega dt is given by f naught upon m omega square minus omega d square whole square plus omega d square b square whole power 1 by 2. Here omega is the natural frequency of oscillations. Now, based on the relation between omega and omega d, that is natural frequency and frequency of driving force, there are various cases. Let us see them one by one. The first case is the damping is small. That means the force exerted is small and the driving frequency is far from the natural frequency. In that case, omega dV is very less than m omega square minus omega d square. So it can be neglected in the equation of amplitude. The equation of amplitude was A is equals to f naught upon under root m square omega square minus omega d square whole square plus omega d square b square. So this term can be ignored. So we can write the amplitude will be equal to f naught upon m into omega square minus omega d square. In this case, the amplitude will be maximum when omega d by omega ratio is 1. That means both the frequencies are same. This condition is called the resonance condition. So, when the frequencies are same, then amplitude will be maximum. This is resonance condition. The amplitude will tend to infinity when the driving frequency is equal to natural frequency. But this is the ideal case. For example, in the swing, when the timing of our push matches exactly with the time period of the swing, we can get the maximum amplitude. But this is not infinity, as there is always some damping. Now, let us see the second case, in which the driving frequency is close to natural frequency. When driving frequency is much close to natural frequency, that is omega d is close to omega, then the term m omega square minus omega d square is very less than omega d b. So the amplitude will be f naught upon, we can ignore this term, omega d b. So this will be the amplitude in the case of both are almost same. The maximum possible amplitude for given frequency is controlled by the driving frequency and the damping, and it is never infinity. The phenomenon of increasing amplitude when the driving force is close to natural frequency of the oscillator is called resonance. For example, in the case of swing, we can swing to greater heights if the rhythm of pushing against the ground is synchronized with the natural frequency of the swing. Now, to understand that, let us consider a set of 5 simple pendulums of assorted lengths suspended from common rope. The pendulum 1 and 4 have the same length and the other 5 have the different lengths. Let us set pendulum 1 into the motion. Its energy gets transferred to the another pendulums through the connecting rope. So they also will start oscillating. The frequency of the driving force is the frequency with which this pendulum 1 is oscillating. So this is the source providing the driving force. Pendulum 2, 3 and 5 first start oscillating with the natural frequencies of oscillation and different amplitudes, but this motion is not sustained. Ultimately, they oscillate with the frequency of pendulum 1, that is the frequency of the driving force, but with different amplitudes. They will oscillate with small amplitudes. The pendulum 4 oscillates with the same frequency as that of pendulum 1. As the length of both the pendulum are same, their frequencies will be same, as the frequency of pendulum 4 is matching with the frequency of driving force. So the amplitude of this fourth pendulum will be maximum compared to 2, 3 and 5th oscillator. Let us see some examples based on energy and the oscillations, damped oscillation and forced oscillations. In this example, for the damped oscillator, the mass of block is 400 gram, spring constant is 45 Newton per meter, and the damping constant B is 80 gram per second. We want to find the time period for this oscillation, time taken for amplitude to drop to half of its initial value, and the time taken for mechanical energy to drop half of its initial value. So first, let us find the time period. K into M will be 45 into mass will be 0.4 kg, that will be equal to 18 kg Newton per meter. So root km will be equal to 4.243 kg per second. Now B is very less than root km. So the time period is given by 2 pi under root m by k. That is 2 pi under root 0.4 divided by 45. So time period will be equal to approximately 0.6 seconds. Now we want to find the time taken by amplitude to be half. So t half will be equal to log 2 divided by b by 2m. So that will be 0.693 divided by 0.08 divided by 2 into 0.4. So the t half will be 6.93 seconds. Now the time taken for mechanical energy to drop to its half value, then E of t half upon E of 0 is equals to e power minus b t half by m. So half is equals to e power minus b t half by m. Taking natural log both this side, we can write ln 1 by 2 is equals to minus b t half by m. So simplifying this, we will get t 1 half is equals to 0.693 into 400 gram divided by b, that is 80 gram per second. So t half will be 3.46 seconds. So energy will be reduced to half of its value in 3.46 seconds. In this example, the potential energy of particle of mass 100 gram moving along x-axis is given by u is equals to 5x into x minus 4. We want to find the period of oscillation. The relation between force and energy is F is equals to minus del U by del X. So force will be equal to minus of d by dx of 5x square minus 20x. So force will be equal to minus of 10x plus 20. The acceleration will be force upon mass. That will be equal to minus 10x divided by 0.1 plus 20 divided by 0.1, as mass is 100 gram, that is equals to 0.1 kg. So A will be equal to minus 100x plus 20. Comparing this with basic equation omega square x, so omega will be equal to 10 and omega is 2 pi by t. So time period will be 0.2 pi seconds. So this will be our answer. In the next example, the variation of potential energy with position is plotted. From this graph, we can see the maximum potential energy is 1 joule and the amplitude is 0.2 meter. The mass of the object is given 4 kg. We want to find the time period. The maximum potential energy is equals to maximum kinetic energy and it is given by half k a square, and k is under root omega by m. This maximum energy is 1 is equals to half k can be written as under root omega by m, that is 4, and amplitude square, that will be equal to 4 by 100. This 2 will get cancelled out. This 2 will also get cancelled out. So root omega will be equal to 100. So omega will be equal to 10 power 4. Omega is 2 pi by t is equals to 10 power 4. So time period will be 0.2 pi millisecond. So this will be our answer. In this example, a block whose mass is 2 kg is fastened to a spring whose spring constant is 100 Newton per meter. Now it is pulled to a distance of x is equals to 0.1 meter from its equilibrium position. We want to find its kinetic energy when it is at 0.05 meter. The omega for the block is under root k by m, that is equals to under root 100 by 2, that is 25 into 2, so 5 root 2. That will be equal to 7.07 radian per second. Now its displacement at any time x of t is a cos of omega t, that is equals to 0.1 cos of 7.07 t. When the particle is at 0.05 meter away, we can write 0.05 is equals to 0.1 into cos of 7.07 t. So we can write cos of 7.07 t is equals to 0.5. That is 1 by 2. So this value will be pi by 3. So sine of 7.07 t will be equal to root 3 by 2. Now velocity of block at this point will be a omega sine omega t. Amplitude is 0.1, omega is 7.07, and sine omega t is root 3 by 2. Simplifying this, we will get v as 0.61 meter per second. So the kinetic energy will be half mv square, that is half mass is 2 and v square is 0.61 square. So the kinetic energy will be approximately 0.37 joule. In this example, a particle of mass 0.2 kg is executing SHM of amplitude 0.2 meter. When it passes through the mean position, its kinetic energy is 64 into 10 power minus 3 joule. We want to obtain the equation of motion given the phase is pi by 4. Here A is given 0.2 meter. The kinetic energy is half m omega square E square. Because it is given at the mean position, this will be the maximum kinetic energy. Kinetic energy is given 64 into 10 power minus 3 is equals to half into mass is 0.2 into A square that will be equal to 4 divided by 100 into omega square. This 2 will get cancelled out. This 1000 will get cancelled out. So omega square will be equal to 16 and omega will be equal to 4 radian per second. So the equation is A cos of omega t plus phi. So x will be equal to 0.2 cos of 4t plus pi by 4. In the next example, a body is executing SHM. We want to find the ratio of kinetic energy to the potential energy at x is equals to a by 2. The total energy is kinetic energy plus potential energy is equals to half Ka square. At x is equals to a by 2, the potential energy is half kx square, that is equals to half Ka square by 4. So the kinetic energy is total energy minus potential energy, that is half Ka square minus 1/4 of half Ka square. Taking this half Ka square common, 1 minus 1 by 4. So that will be 3 by 4 into half Ka square. This is the kinetic energy and this is the potential energy. So taking the ratio of kinetic energy to the potential energy, 3 by 4 half Ka square divided by the potential energy, 1 by 4 half Ka square, that will be 3. So ratio will be 3:1. In this example, a simple pendulum of mass m executes SHM with total energy E. If at an instant one of extreme positions, then linear momentum after the phase shift of pi by 3 radian will be. The energy is at an instant is, let's say, E naught. So energy at particular phase shift will be given by E is equals to E naught cos square phi. That will be E naught. Cos square pi by 3. E can be written as P square by 2m is equals to E naught is given E and cos square pi by 3 will be 3 by 4. This 2 will get cancelled out. So P square will be equal to 3em divided by 2. So P will be equal to under root 3em by 2. In this example, in damped oscillations, if the amplitude becomes half of its maximum value in 1 second, then after 2 seconds, the amplitude will be. In the damped oscillation, if after t time, the amplitude becomes a by n, then after 2t times, the amplitude will become a by n square. After 3t times, the amplitude will become a by n cube, and so on. Here, after 1 second, the amplitude is half, that is a by 2. So after 2 into 1, that is 2 seconds, the amplitude will be a by 2 square, that will be a by 4. So this will be our answer. Remember this as a shortcut. Now, in the next example, A particle is performing SHM with energy of vibration 90 joule and amplitude 6 centimeter. When the particle reaches at a distance of 4 centimeter from mean position, it is stopped for a moment, then released. We want to find the new energy of vibration. Here, the energy is 90 joule and the amplitude is 6 centimeter. The maximum energy is half m a square omega square, that is equals to 90. So from this we can write m omega square is equals to 90 into 2 divided by 36 into 10 power minus 4. So m omega square will be equal to 30 into 10 power 2. Now, when particle is stopped, at x is equals to 4 centimeter, the new amplitude A dash will be equal to 4 centimeter, but omega angular velocity will remain same. So in that case, energy will be half m a dash square omega square, but m omega square is 30 into 10 power 2 into half a dash is 4 centimeter, that is 16 into 10 power minus 4. So that will be 240 into 10 power minus 2. The energy will also remain same as the conservation of energy. So energy can also be written as, we want to find here the amplitude. So energy is 90 joule so that will be 30 into 10 power 2 into m omega square half a2 square, that is equals to 90 joule. So a2 square will be equal to 4 into 10 power minus 2. So here the energy is half m a1 square omega square. Now when the amplitude is changed, the energy will change, but this m omega square will be constant. So E1 is equals to half m E1 omega square and E2 will be half m E2 square omega square. Taking the ratio, we can write E1 by E2 is equals to A1 square by A2 square. E1 is 90 divided by E2 is equals to A1 square, that is 36 into 10 power minus 4 divided by A2 square, that is 16 into 10 power minus 4. So E2 will be 90 into 16 divided by 36. This 9 4s are 36. So E2 will be equal to 40 joule. So instead of finding the m omega square, taking the ratio will be better option. Here the key concept was the m omega square will be constant. That means for given oscillation, omega is independent of amplitude. So this is for all today. Thank you.